right. Hello, folks. My name is Hannes, and here with me today is Nadia. Hello, Nadia.
Hi.
And Nadia and myself, we work on Jira, specifically on Jira's new React-based modern UI. And Nadia and I obviously are not alone in doing that, so there are a few more of us, more than 500 to be exact, that operate on the new code base. And the new code base is now well above 1.5 million lines of code. So when we talk about scale today, this is what we mean. But we're going to do it a little bit differently today. We're going to go way beyond software engineering. We're going to talk about economics. We're going to talk about politics. We're going to talk about philosophy. Nadia, shall we do it? I think we shall. All right, so I'm going to start this story almost 200 years ago with a guy named William Forster Lloyd. This, by the way, is not William Forster Lloyd. I didn't find a picture, but he could have looked like this, right? William Forster Lloyd was telling the story of a village in England, and in this village there were 3 farmers. Let's call one of them Hannes. Let's call one of them Nadia, and let's call one of them Chad Watson. And a little bit outside of this village, there was a field. And that field belonged to nobody and everybody, right? It was a common ground. And so what our farmers are doing is they send their cows there. That makes a lot of sense, right? There's a field, let's send our cows there. But the interesting thing is that for every farmer, for every individual farmer, it always makes sense to send another cow there, right? Because they get the full benefit of that cow, but the cost of that cow, as in the grass that cow is eating, that is shared across everyone, right? So it always makes sense for folks to add another cow. And then it makes sense to add more cows, right? For every individual, this always makes sense. And at some point, the folks will maybe realize that the cows are getting a little bit smaller and a little bit skinny, right? Because there's not enough grass for all of them. But still, at any point in time, for every individual, it's still beneficial to send another cow to that field, right? So we keep sending cows, until one day the whole thing turns into a post-apocalyptic wasteland. Why is that? Because we're dealing with a shared, limited resource, right? It's shared across all the villagers, but it's limited by the amount of grass that it gives to our cows. This story was picked up roughly 100 years later by a guy called Garrett Hardin, who called that the tragedy of the commons in a Science magazine article. And what Hardin says is, well, this applies to cows, but it also applies to deforestation. It also applies to overfishing. It applies to traffic. It applies to air pollution. It applies to light pollution. It applies even to our email system. So today, Nadia and I, 2020, we are here to say this applies to software engineering too. February 28, 2020, ReactConf EU. Not the Science magazine, but you got to start somewhere. So if you think about it, we're dealing with a shared limited resource. But if you think about it, so is our code base, right? It is shared across all our engineers, but it is limited by the complexity that our brains can process and can deal with, right? So for every individual engineer, it always makes sense to add a new cool engineering pattern or do a workaround or do some kind of a creative solution. But if we all keep doing that, we will hit a limit. The second shared limited resource that we're dealing with is the browser, right? Shared across all the code of our application, but limited by the amount of CPU, amount of memory, amount of network bandwidth that the operating system is assigning to us. So sure, right, for me as a developer, it's always beneficial to add my feature, right, to add another feature, to add another feature. But if we all keep doing that, right, we will end up in a post-apocalyptic wasteland. So let's get into solution mode. And the way we want to do it today is we will always talk about our villagers example, right? And we will see how this maps into modern software engineering. So let's start with our villagers, and what Garrett Hardin actually proposed in his article, and you don't necessarily need to agree with that, but he proposed that maybe we would be better off if there was no common land, right? Maybe we would be better off splitting the Singed Bard into 3 fields, each of them belonging to a farmer, would still be limited, but it would not be shared, right? And Nadia could, build her mill, and I could drive around with my truck, and Chad could have some cows. So Nadia, this model of splitting this apart, how does that work in software engineering?
Such an interesting question, Hannes. Let me explain it to you. So what separating fields for farmers in software development we call modularization. And in JavaScript land, for separating our code into independent units, we have different ways to do it. We have functions, we have components, we have files, and of course we have something that is called packages. And packages is a concept that is quite familiar to library developers. We publish those packages on NPM, we consume them from them, and it's quite easy and natural to write and think about our code as just a set of packages. For product development, the concept of packages is not that familiar, because when we write our product, our code ended up, we bundle our code as a big, huge chunk of JavaScript, and then we send it to the browser, where it's consumed by the end user. So it's also quite natural and tempting for us as product developers to think about our source code as also a big, inseparable unit of something. And this model can work for a while, as long as your product is small and tiny and as cute as this tiny little fish. But if your product continues to grow, eventually we all know what will happen. This fish will turn into something like that. So essentially, instead of this, inevitably, we will get something like this. And then this, and then we will end up in a world like this. So what we as software developers need to do is to do exactly the same thing as farmers can do and build some sort of fences, build composition boundaries within our product. And if we, as product developers, instead of thinking of our code as big inseparable chunk, inseparable unit of something, think about it as a composition of packages with clearly defined APIs and dependencies, clearly defined dependencies between those packages, it will also make it much, much easier to think about our code as just a set of packages, where every package is just a clear module, clear component boundary. And then, same as with our villages, our software developers can just take care of their own small, tiny field, their own small, tiny package, and then don't really worry about what is going on the other side of this fence.
Well, that's very interesting, Nadia. Thank you for sharing that. I have a question though. So if you look at our village in England, you may notice that one of these fields is a little bit larger than the others, right? I think it's Chad Watson's field, and you can easily get some kind of a strategy of the comments on that unit in itself, right? So it may be a good idea to actually split that one in 2 halves later on and just pull up a new fence. Nadia, how does that work in engineering?
Another excellent question. And in engineering, it works almost exactly the same way. Only instead of splitting up existing fields, we call it embracing a component mindset. Because we are in React, we are writing code in React, we love React, and React built from the ground up with the composition in mind. And as a consequence, it makes it really, really easy to compose your app together and, again, decompose your app together into independent pieces. Which is really cool, but for us, unfortunately, not as much, because we have to deal with a lot of non-React code in our applications. Because we started with a state management solution that is not React. We started with Redux. And so we ended up in the world where our apps structured something like this. We have beautiful components, composition patterns, and then we have this huge, big monolithic Redux store that sits outside and then spreads its tentacles everywhere, and everything behind this beautiful components composition is just mashed together. And if we want to visualize this picture, it looks probably something like this. On the surface, we see those clear, beautiful trees, and it looks like it's really, really easy to just move one tree outside of another tree into some other place, and everything is cool. But if we start digging a little bit deeper, we will see something like this. Underneath, all those trees, all those roots of those trees are really mangled together. So for us to embrace composition model, we needed to rethink our state. We needed some sort of state that is basically loved by React, that is modular, composable, and also future-proof, in the sense that it can be evolved with the way React evolves, and we should be able to consume new React features seamlessly and without much effort. When we started thinking about it, we took a closer look at what is going on in our Redux stores, and we figured out that Redux actually solves at least 3 different problems for us. Redux solves for us local state management, it solves for us shared state management, and also remote state. So let's take a closer look at those states. First of all, local state. We have a component, and then this component has a bit of a state, and actually that is the end of the story because there is nothing more to it. Local state is the simplest one of all. You just use state, and that's it. We tend to sometimes shove this into Redux, but again, it's really unnecessary. With the shared state, it's a little bit more interesting. Shared state is a situation when we have a couple of components and they are interested in sharing some piece of information between them. So one way to do it would be we can extract this piece of information to the closest parent and then share from this parent to those children. In a model like that, it probably will work with just props. Your parent can just pass props to children and everything is, again, very simple. But more often than not, you will find yourself in a situation where between this parent and those children, we have layers and layers of components that don't really need to know about this state, and they don't really care about this state. Luckily for us, React provides us a really nice escape hatch, which is called React Context. With React Context, we can just pass all those layers of components that we don't care about and just consume this state directly in those children. And implementation-wise, it will look something like this. We'll have a cows provider somewhere at the top. We will have layers of those components that we don't care about. And then at the exact point where we care about cows, we will just consume this API. We will be able to watch those cows, add or remove them, or do whatever we want with cows. And then there is a remote state. Remote state is also interesting, and it's quite similar. We have a bunch of components, and they want to consume a piece of data, piece of information. Interesting thing here is that in this case, this piece of information lives somewhere outside of our UI, somewhere in the remote endpoint, and can be consumed only through REST and or GraphQL request. So how we can solve this? Exactly the same way, we can introduce a parent component, the only purpose of which is to just call this REST endpoint and get this data and then share it with its children. And implementation-wise, again, it will look almost exactly the same. We will have cows provider somewhere at the top. We will have layers of components, and then at exactly the same time where we want this information, we will just use this API, which might look familiar to some people here because we kind of borrowed it from Apollo, and the concept of loading year and data is something that is really common in Apollo and GraphQL world. But this is not tied in any way neither to GraphQL, neither to Apollo. We can just abstract common REST request under exactly the same API. So context solves those problems for us. Context is awesome. And of course, with great power as we all know, comes great responsibility, because in case of context, it comes with a couple of gotchas. The very first one that we saw really early on is what is called provider's hell. In a situation when you have an app that is slightly larger than a tiny form, you will see probably something like this. We have a provider, and then a provider, and then another provider. Lots of providers everywhere. And this is not really cool by many reasons. And one of them, the most important one of them for us, was that it's really, really easy to, when you're implementing all of this, to make a mistake and to write code that will cause all consumers of a provider to be re-rendered on almost every movement, like a mouse draw. So context is awesome. It comes with a lot of good stuff, but also with some not really good stuff as well. And when we started thinking about it, we actually noticed that it's exactly the same story with Redux. Redux comes with some benefits, like, for example, ability to select piece of state or structured approach to state management, but also with lots of baggage that we don't really care about. So we, again, did a bit of thinking in Atlassian, and we thought, what if we kill all this smelly part and then just implement something that is good and take good from both worlds? And that's exactly what we did. We implemented our own state management solution. It's really sweet, and it's even called React Sweet State. It's open source, so it's really cool. Please check it out and give us feedback if you like it, or if you don't. But you will like it, I promise. So where it actually leaves us? It leaves us in the world where we have this React beautifully structured and composed components everywhere, but we actually don't have this monolithic Redux store underneath that ties everything together and glues everything together. We still have state, it's here and there, but if we think that this particular app becomes big and needs to be decomposed, it's really easy. We can just cut all connections in certain places and just decompose it into a completely different app, and that's as easy as that.
Well, that sounds very interesting, Nadia. Thank you again for sharing that. I do have a comment though and a question. So I think we can pull up all the fences, we can do all the modularization, but I think it only gets us to a certain point, right? So let's imagine that on our beautiful field, we have this lake in the middle, beautiful, right? We split it up, but now let's imagine that one of our farmers is actually a bad actor and decides, you know what, I'm gonna spill all my old oil into this lake. And obviously that's not a great situation, right? It's not great for that cow that is grazing peacefully there. It's actually a pretty sad cow. I mean, let's zoom into that. Look. That's an unhappy cow, hey? So that's not cool, right? Like, we can't do that. And the other thing that we need to take into account is, we're doing business here, right? Like, we need to optimize for the overall productivity of all our villagers, right? So imagine the queen, right? Back then I think it was Queen Victoria, and you can see she is not amused, right? Because what she's saying is, look, Hannes, you have this truck full of crops. Why the hell would you not bring this truck to the mill, right? Why the hell would you not open a gate here, drive through? So how do we solve situations like that? Well, I think in the history of mankind, right, the only real way for us to sustainably deal with a shared limited resource was through rules and conventions. Right? That farmer can't spill the oil into the lake because it is illegal to do so. Right? There's a law against it. That's what I mean by rules and conventions. Right? So Nadia, how does this concept apply in the software engineering world?
To software engineering world, it applies in almost exactly the same way. Same as farmers have laws, we also have our own rules and conventions. So just to give you a couple of examples what I mean by that. Remember, we have packages. And it's totally cool and totally valid for one package to import something from a defined API of another package. Why not? That's what they designed for. But it's totally not OK and highly discouraged for one package to reach deep inside another package and steal something from it. It's a no-go. Another example will be we are very opinionated on how you should manage your state management components. So, for example, it's totally valid, again, for a visual component to take advantage of a remote and or shared state component. But it doesn't really make sense for a component that only implements fetch request and only manages REST requests to import something from a visual component. So those are our rules and conventions. And the way we implement them is through tooling. We are in Atlassian obsessed, borderline obsessed with all forms of static code analysis. And first and foremost, of course, ESLint. ESLint is our holy grail. We implemented lots of custom ESLint rules that enforce all of those rules and conventions for us. And a second quite interesting tool that we have is called Stricter. Stricter is something like a ESLint only on your project level. It's like ESLint for your files, for your project. It's also developed in Atlassian, and it's also open source. So check it out. It's also really cool. And again, same story as with farmers. You can do with tools with static code analysis so much. Same story as with farmers. We need some sort of police enforcement to make sure that all those rules are obeyed. And in Jira, we have a platform team that operates sometimes as those cops. And this platform team makes sure that everything is in order and everything makes sense in our repository. And again, exactly the same story as with farmers and real policemen. This police cannot operate on their own will. They need some sort of written law according to which they operate. And the role of this law for us plays something that we call tech stack. Tech stack is a set of conventions or use cases that we have in Atlassian. So, for example, as a developer, I want to have type safety, or I want to structure my components, I want to respect package boundaries, all those interesting use cases. And the most importantly is those use cases are supported by tooling or different libraries to solve this use case. And interesting thing here is those use cases are encoded. They live in code. And this allows us to implement very different and interesting automations on top of it, including generating this beautiful website.
All right, Nadia, this is great. Let me play this back to you. Yeah. So, as a society, we are exposed to shared limited resources, right? It can be a field in a village in England. It can be the ocean. It can be the atmosphere, right? And I think it's a struggle as old as mankind to sustainably manage these shared limited resources, right? As engineering teams, we're exposed to shared limited resources too, right? Our code base is limited by the amount of complexity that our brains can deal with and can process. The browser is limited by the amount of CPU and memory and network bandwidth that the machine assigns to us. Luckily, we can take some of these learnings, right, of hundreds of thousands of years of dealing with shared limited resources and apply them to software engineering. So we were talking about splitting up fields, right, and essentially pulling up some fences. We do something very, very similar when we modularize our software. When we were talking about, recognizing that some of these fields are maybe getting a little bit large and maybe we should split them down further, right? Well, we can absolutely do that, but we need to embrace a component and a composition mindset. And finally, modularization, pulling up fences, it will only get us that far, right? Like we need certain rules and conventions that we can play by, and that applies to dealing with a field in an English village as much as to front-end development. So at the end of my presentation, as an Austrian, right, I would love to quote one of the great Austrian philosophers, but today I need to quote a German one, Friedrich Engels, who says that freedom is the recognition of necessity. And I really like that, right, because we all want to be free. Right? It's arguably the most important thing to us. This is what makes us human, right? I want to be free to farm my cows. Right? I want to be free to introduce a new engineering pattern. But we need to recognize and we need to acknowledge that we are all in this together, right? So my personal freedom can only go so far that it does not restrict the freedom of others or of the society overall. That's the reason why my little baby sister, 10 years old, right, she is not free to grab a Snickers bar in a shop and not pay for it, but she is free to become an astronaut, right? So, thank you very much.